Hey everyone, and welcome. Today we are talking about something huge, a genuine revolution that's happening in science as we speak. We're talking about completely tearing up the old rulebook for how we discover new medicines. Forget the old, slow, and frankly, often disappointing methods. We are entering a new age, one that's being powered by some seriously futuristic tech like artificial intelligence and quantum computing. So let's jump right in and see what this new era of medicine is all about.
So to really get why we need this revolution, you first have to understand the problem. And honestly, this number says it all. $2.8 billion. That is the average cost to bring just one new drug from a lab bench to your local pharmacy. It's a mind-boggling amount of money, right? And it's a huge wall standing in the way of innovation. But believe it or not, the cost is only half the story.
Because here's the other half, the failure rate. After spending all that time, all that money, 9 out of every 10 drugs that look promising enough to even start human trials, they fail. They just don't work or they're not safe. So just think about that for a second. You spend maybe a decade and billions of dollars on a project that has a 90% chance of being a complete write-off. It's kind of insane. The traditional system is broken, and it is absolutely begging for a change.
So what do you do with a broken system? Well, you don't just patch it up. You rewrite the entire playbook. And that is exactly what our first big game changer, artificial intelligence, is doing. And look, this isn't just about making the old process a little bit faster or a little bit cheaper. No way. This is a fundamental shift in how we even think about the biology of a disease.
For the longest time, drug discovery was pretty much just trial and error, a bit of a guessing game. We had some incredible breakthroughs, don't get me wrong, like AI that could predict the 3D shape of proteins. Those are the little machines in our cells that diseases often mess with. And that was like figuring out the shape of the lock. But the real problem, the big challenge was, how do you find the key for a brand new lock you've never even seen before? That takes a whole other level of intelligence.
And that's where this critical idea of generalization comes in. It's all about an AI's ability to solve problems it wasn't specifically trained on. For drug discovery, this is the holy grail, because diseases are always throwing new biological puzzles at us. And this is where the next generation of AI is just blowing the doors off. A perfect example is a platform from Isomorphic Labs called the ISO-DDE, or Drug Design Engine. It was built from the ground up specifically to tackle the unknown.
And we are not talking about small, tiny improvements here. Look at this table. We're talking about a massive, massive leap forward. When you test this thing on its ability to generalize to new types of drug molecules, ISO-DDE is more than twice as accurate as its super famous predecessor, AlphaFold 3. For complex antibodies, 2.3 times better. And in some really specific, high-accuracy situations, it's almost 20 times more predictive. This is not an upgrade, folks. This is a completely new kind of tool.
So what can you actually do with all this new power? Well, for the first time, we have an AI that can predict not just if a drug will stick to its target, but how tightly it will stick. That's huge. It can also find brand new cryptic pockets on a protein. These are places to attack a disease that were literally invisible to us before. And it does all of this at a tiny fraction of the cost and time, turning what used to be a years-long manual process into this super-fast automated design loop.
Okay, so the AI is giving us these super precise targets. Amazing. But that brings up a really interesting question. What if the best way to fight a disease isn't just to block the bad guy, the bad protein? What if we could just get rid of it entirely? This line of thinking has led to a completely revolutionary new class of medicines that don't just slow disease down, they tell our body to take out the trash.
And this is the central idea behind a strategy called targeted protein degradation, or TPD. So instead of creating a drug that just gets in the way of a harmful protein, TPD lets you design a molecule that basically puts a "destroy me" sign on it, and then it just steps back and lets our body's own natural waste disposal system do all the heavy lifting. It's a seriously clever approach. And this shows the two many ways we can do this, and they're both brilliant. On one side, you've got PROTACs. The best way to think of these is like a molecule with two hands connected by a rope. One hand grabs the bad protein, the other hand grabs the cell's disposal crew, and the rope just pulls them together. Then you have molecular glues. These are smaller, and they act more like a dab of superglue. They change the surface of one protein so the other one just naturally sticks to it. Two different methods, same awesome result. The target gets destroyed.
And the system these drugs are hijacking? It's called the ubiquitin proteasome system. Here's how it works. First, the drug brings a special enzyme called an E3 ligase right up to the target protein. That enzyme is like a little tagging gun. It shoots a molecular tag called ubiquitin onto the protein.
Think of it like a kick me sign. The cell's recycling center, the proteasome, sees that tag and knows exactly what to do. The tagged protein is shredded, and here's the best part. The drug molecule is totally unharmed. It can just go off and do the whole thing over and over again. It's incredibly efficient.
All right, so we have AI to find the targets, and we have these slick new drugs to get rid of them. But there is one more piece to this amazing puzzle. Because even though AI is fantastic at spotting patterns, when you get down to the tiniest scales, all of chemistry and biology is run by the super weird rules of quantum mechanics. And our computers today, they just can't handle it.
This is what scientists call the exponential wall. See, a molecule's behavior depends on how all of its electrons are interacting with each other, and trying to calculate that, even for a medium-sized drug molecule, is a problem so ridiculously complex that it would take a normal supercomputer longer than the entire age of the universe to solve. So, to really simulate reality, we need a completely new kind of computer, one that actually plays by reality's own rules.
And that brings us to the core difference between the computers we use every day and quantum computers. Your laptop uses classical bits. They're simple. A bit can be a 0, or it can be a 1. A switch is on, or it's off. But a quantum bit, or a qubit, is special. Thanks to a wild property called superposition, it can be a 0, a 1, or both at the very same time. This lets a quantum computer explore just a mind-boggling number of possibilities all at once, which is pretty much exactly what molecules are doing in the real world every second.
And hey, this isn't just theory or science fiction anymore. This is happening right now. A perfect example is India's incredible investment in the Amarvati Quantum Valley. This is a massive project backed by the National Quantum Mission, and its goal is to create the country's first real quantum ecosystem from the ground up. It's going to house an IBM Quantum System 2, the most powerful one in the entire country, and it's set to go live really, really soon.
I think this quote from Andhra Pradesh's Chief Minister N. Chandrababu Naidu really says it all. The ambition here is just huge. This isn't just about building one fancy computer. It's about launching an entire industry, sparking new innovation, and making a real play for global leadership in a technology that is absolutely going to define our future. Okay, so we've looked at 3 incredible, game-changing revolutions that are all happening at the same time: predictive AI, protein-degrading drugs, and quantum computing. So now let's put it all together. Because their real power, the true magic, isn't what they do alone. It's in how they're starting to work together to create something brand new. I want you to just imagine this incredible feedback loop. You have the AI designing billions of potential drug ideas entirely inside a computer. Then you have these new types of drugs, like protacs and molecular glues, that let us go after targets that we used to think were completely undruggable. And finally, you have quantum computers that can simulate how those drugs will actually behave with perfect accuracy, letting us know what works before we even step into a lab. You see? Each piece of technology makes the others even more powerful. So what's the end result of all this? Well, it's a complete collapse of the old drug discovery timeline. We go from that long, slow, incredibly expensive, and high-risk process you see on the left to a new world that's fast, targeted, predictive, and just wildly more efficient. We're talking about finding cures faster and cheaper than ever before. And that really leaves us with one last, and I think incredibly exciting question to think about. In a world where we can use AI to design the perfect drug, use revolutionary chemistry to build it, and then use a quantum computer to test it against the fundamental laws of physics, what does that actually mean for all of us? What diseases, what conditions that we've been fighting for centuries might finally become a thing of the past? The possibilities are just staggering to think about. Thanks so much for joining me.